In this lecture, we will review some general properties of a qubit that will be useful for us to proceed to the discussion of quantum information. To do this, we start from comparing a qubit to a classical bit and a classical random process. We will highlight the key similarities and differences between them. A classical bit can be in two possible states, either 0 or 1, which are the basis for classical computation. Building on this, a quantum bit, namely a qubit, also have a set of two states as the computational basis, labeled as state 0 and state 1. This symbol, the so-called cat, is a notation used for the indication of a quantum state. However, different from a bit, a qubit can be in state 0 or 1 or any linear combinations of the two, any linear combination with complex coefficients. Here let's look at a commonly used analog. Let 0 and 1 be the label of head or tail for the face of a coin. When we read out the result of a coin tossing, we get one bit of information, that is, head or tail. However, during the process of the tossing, we do not know whether we will get head or tail. If this is a perfect coin that is tossed fairly, we have 50% to get either head or tail. That we can say the state of the coin is a mixture of 0 and 1 during the process. A qubit has the intrinsic property that it can be in the mixture of state 0 and state 1. The quantum mixture of the qubit can be more evolved than just a coin tossing that we refer to as the superposition. A quantum operation operates directly on the superposition state, which can be understood as parallel operations on 0 and 1 states. If we denote a qubit state by state psi, then psi equals to alpha 0 plus beta 1, where alpha and beta can be any arbitrary complex numbers. We say that the qubit is in the superposition state of 0 and 1. For convention, we choose to normalize the state with alpha squared plus beta squared equals to 1, so that alpha squared is the probability of finding the qubit in state 0 and beta squared is the probability of finding the qubit in state 1. The sum of the probabilities add up to 1, as it should be. Since alpha squared and beta squared are probabilities, we refer to the complex coefficients alpha and beta as probability amplitudes. Given the normalization, we can equivalently use the spherical coordinates to represent the qubit superposition as this, where theta and phi are between 0 and 2 pi, which uniquely define the state. The probabilities for the state to be in state 0 or 1 is given directly by cosine half theta squared and sine half theta squared. And phi is the complex phase. This representation leads to the definition of a Bloch ball that helps in illustrating qubit operations. We will talk more about the Bloch ball later in the course. Going back to the analogous coin tossing example, different from a coin, a qubit can exist in a continuum of superposition states between 0 and 1. There are two keywords in this statement to be emphasized: continuum and superposition. For a perfect coin that is fairly tossed, the probability of getting head is 50%. If the coin is not perfect, or if the tossing is biased, one might be able to get any probability between 0 and 100%. An extremely good magician can do that. For this, we can say that the probability distribution of coin tossing can be continuum if the coin can be tossed an infinite number of times. We also see directly from the qubit formalism that the probability distribution of a qubit in state 0 or 1 is continuum. This originated from the continuum in the parameter space of the probability amplitudes, which can be any complex number in the unit circle. The introduction of complex numbers for the description of qubit is counterintuitive to our common sense, and this is one of the major differences between the quantum world and the classical world. At any moment during a coin tossing, the state of the coin can be described by p times head plus 1 minus p times tail, where p is the probability of getting head. We call this a classical mixture. Such classical mixture is analogous to the state psi c in the quantum description. By contrast, a superposition state has a much richer structure. Before measurement, a qubit can be represented by the state alpha times 0 plus beta times 1, which is a superposition state between 0 and 1. Its density operator is represented by the equation here, which has 4 terms instead of only 2 terms for the previous case. In the matrix representation, the last 2 terms are the off-diagonal elements that keeps the quantum coherence. In the presence of noise, the quantum coherence of the qubit can be destroyed and end up as a classical mixture. Next, let's consider other differences between a qubit and a classical bit regarding measurements. A classical bit, such as a coin, can only be measured in one basis. That is the basis the classical information is carried in: 0 or 1, head or tail. By contrast, a qubit can be in any superposition state and can be equally well represented in any orthogonal basis. Then, which basis should we use as the computational basis? Let's don't forget that qubits are abstract representations of real quantum systems. There are many different physical systems that can be used to realize a qubit. For example, the polarization of a photon, the ground and excited state of an atom, the spin up and spin down state of a nuclear. Computational basis is often chosen to be the basis in which it is most convenient to implement physical measurements and other operations. We label them by state 0 and state 1. So, practicality is the main consideration here. Measurements in the computational basis are realized by projecting the qubit state into the basis 0 and 1, represented by the 2 measurement operators π0 and π1. The measurement probabilities are given by the Born rule. The probability of finding the qubit in the state is the trace of the product of the measurement operator and the state. The expressions of P1 and P0s are shown here. The 2 probabilities add up to 1 as it should. Other than measurement in the computational basis, we can also do projective measurements in any other basis, or even non-projective measurement. This provides us tools to distinguish by measurement the quantum coherence from classical mixtures. Well, one might ask, how much information is represented by a qubit? Paradoxically, there are infinitely many different qubit states, given by a continuum parameter space. Each one of the parameters can store an enormous amount of information. However, not all this information are physically accessible. Each measurement of the qubit only gives one classical bit of information. For any qubit, measurement in the computational basis give either 0 or 1. One side of this is analogous to the coin example, as a coin can be prepared or tossed in a way that has probability p of giving head. Theoretically, p can be a number between 0 and 1 with many decimal places, but only the final result of head or tail is that one bit of useful information. Can we read more information from a qubit rather than just one bit? The answer is certainly yes, but that requires repeated measurements on the same quantum systems. The other side of this that is completely different from a coin tossing is the unpredictability of the measurement result. If one knows exactly how a coin is constructed, its initial state, the force on the coin, and all other information that is related to the procedure, one can know, in principle, exactly whether the outcome would be a head or tail. However, if the qubit is prepared in the superposition state, such as 0 plus 1 divided by square root 2 shown here, it is impossible to predict the outcome of each measurement. We can only say that there is 50% of chance of getting 0 and 50% chance of getting 1. This is not because of our ignorance, that we don't know enough about the qubit and other related information. That result is simply unknowable. And this is the intrinsic property of quantum mechanics. A very good elaboration on this is the Bell paradox that was discussed in the Welcome to Quantum Mechanics 1 course and a few other videos on the QuTalent platform. We will also have a simple discussion on it later in this course.